Everybody, can you see my screen?
Yes, sir.
Okay. You see that last time we were discussing some questions and problems. Still, we could not finish. So we will be continuing those. Uh, and then after some question, today we will also be solving some numerical problems. So you need your pen, paper, and calculator. Um, you see the first question. In order to improve the transient stability of the synchronous generator, shown in figure 1. This is the figure 1. You choose a series resistor and also a parallel thyristor based resistor to be connected at the secondary side of the transformer. After occurrence of a fault, how would you coordinate their operation? Okay, so you see this is a system, this is a power network. As you can see, leftmost side SG, a synchronous generator. So those values P and V values you see small number 1.0, V 1. Those are actually per unit value, not the actual unit. And then this is the transformer, this side secondary. Secondary side is connected to the grid. There are double line, transmission line, and they are feeding to infinite bus. So that is the configuration of the system. Now, the fault has happened at point K along the transmission line. So keep in mind that although just one line has been shown, but basically it is three-phase system. It is the single line diagram. That's why only one line is shown. Now this statement says, if the fault happened at this point, and then we need to improve the transient stability, and then you want to put two control device on each, you choose a series resistor. So this means definitely this is series connected at the Y side of the transformer, as well as you are putting a parallel thyristor based resistor, which is that breaking resistor that we discussed so far. So definitely that is in parallel. This means you are connecting on series resistance and then you are connecting on parallel thyristor based resistor, which is the breaking resistor. And after occurrence of the fault, how would you coordinate their operation? So meaning that, would you switch in simultaneously? Should you start their operation simultaneously or one at a time? Which one you want to operate first and which one is later? Is it the series resistor or the parallel thyristor based resistor? Now, the context of this question is that, why I am asking in that way. The thing is that series resistor, because it will be connected in series, and easily you can understand that during fault, there will be high value of fault current. So therefore, series resistor, definitely it will suppress the magnitude. It will reduce the magnitude of fault current. That is the objective. And it is connected in series. Of course, you can assume that through a switch. So therefore, during the fault, there is a parallel switch that will be activated and the resistor will be in circuit. And then parallel breaking resistor, which is that thyristor based switching circuit, you noticed before that it is connected in parallel. So typically that resistor is activated after the circuit breaker opening. So the thing is that once there will be fault happen at point K, of course, there are circuit breakers along the line. Those are not shown in the picture, but definitely there are. Those will be open. So that is the first protection. And then followed by that, that series resistor, because it is in series, easily it will work. So the first, that series resistor will work. And then the parallel thyristor based resistor will work. So that is the coordination. So you have to just tell that first series resistor will activate and that will reduce the magnitude of fault current. And next time, after the circuit breaker opening, the parallel thyristor based resistor will be connected and that will improve the active power, P value, and then the overall stability will be maintained. Everybody, could you follow me what I said?
Yes, Dr. Ali.
Yeah. So, I mean, there are two things. One is that series register, and then again there is parallel register, which is the breaking register that we are looking last 2 to 3 classes. So therefore, how would you coordinate? Coordination means would you operate them simultaneously or on at a time? So the answer is on at a time. So I will coordinate their operation by first inserting the series register and then the parallel thyristor. This will be the answer. So therefore, the parallel connected device basically that will control active power and the voltage will return back. Series device will reduce the magnitude of the fault current. In that way, overall stability will be achieved. Okay, so moving forward, question number 2. Again, you see pretty much similar configuration, number 1 and number 2, as you can see, but there is difference. Here it was synchronous generator in figure 1, but here I am putting induction generator. And because I am putting induction generator, you know that I need a capacitor at the terminal point. Okay, now question is, if a three phase to ground fault occurs at point G, this is that point. This means along the transmission line in figure 4 system, then what would be the characteristics of speed, terminal voltage, and output power of the squirrel cage type induction generator? This is the squirrel cage type induction generator. So how does the speed, terminal voltage, and output power will look like? That is the thing. Also, if the input torque of the generator varies randomly, then how would the voltage and frequency of the generator be affected? And how can you ensure the constant voltage and power at the consumer end? So like 3 questions. So first question is that some fault happened. So due to the fault, what would be the characteristics of speed, terminal voltage, VT, and then output power of this induction generator? This is squirrel case type. And the next question is that if the input torque varies, definitely, although it is taking reactive power from the grid, but also it has the shaft, and that shaft is being driven by a different source, different prime mover, because you have to make the slip negative. So that is the input value or the input torque. Input torque of the generator varies randomly. There is a source, power source that is driving the shaft, but that input torque is continuously varying. Under that situation, how would the voltage and frequency of the generator be affected? So therefore, this means that in this case, for the second case, we are assuming that there is no fault. Just the input torque of the generator is varying randomly. Then how does the voltage and frequency profile look like? That is the meaning. And the third question, how can you ensure the constant voltage and power at the consumer's end? Now you see, infinite bus means here the customers will be connected. Now they want always constant voltage and power. So whatever the generator you use, whatever the type is, whatever your input source is, input torque varies or does not vary, they want the constant voltage and constant power. That is their objective only. So how can you ensure? So 3 questions. So first question come back. So if there is any fault, what will be the characteristics of speed, terminal voltage, and output power of the induction generator? So how would you answer? So can you draw their speed, voltage, and output power profile? Everybody, can you follow me?
Yes, Dr. Ali.
Yeah. So this is induction generator, and then the fault happened. So what would be the characteristics? This means how do the speed, terminal voltage, and output power behave? Now, because this is, I mean, although it says a squirrel cage induction generator means its speed is constant, almost constant, because that is the fixed type. It is not the wound rotor type. There are two types. One is called wound rotor type. The speed is variable, and then squirrel cage speed is almost constant. Now the fault happened. So therefore, even the speed is constant, but still the speed will change. So therefore, by the common nature, whether it is induction machine or synchronous machine, the common consequence of any fault is that terminal voltage and output power will go low, and then speed will go high. And the frequency also will go high. That is the common nature. Now, because this is the induction generator, therefore voltage and output power will go fairly low. There will be huge voltage drop. Almost voltage collapse, and drastic output power drop, and speed will go high, significantly high. That will be the characteristic. So what you can do, let me take you to that board. Okay, so you draw with me. For example, this is time. We are plotting the voltage. Now, the voltage was fine. It was initially going fine at steady state. Value was 1.0 per unit, for example. Now, suddenly at this point, at t on time, for example, the fault happened. So therefore, there will be voltage drop. So therefore, it will be the situation in case of the induction machine, because that is the three-phase to ground fault example. So it will be the nature, because you see it does not have any AVR and governor. So it is not like that it will come back and it will settle down. So in most cases, it does not come back because it does not have any control means, unless you put some control means at the grid side, like some additional capacitor, some SBC, some reactive power compensator, STATCOM or other means. It does not come back. So that's why you will be getting this response ultimately. So that is your voltage profile. Similarly, you can draw the active power profile. So this will be your active. So then again the same thing. Initially it was fine, and then it will drop down. So this is your zero value, this is your zero value. So this is that fault point, t on time. Initially, again, for example, it has that 1.0 per unit value, which is the steady state value. And at t on time, suddenly the fault happened. So power profile will go down. And then the speed thing, the speed, which is omega, again, that was constant. For example, speed will go fairly high. It will look like that. After a long time, it will come back, but it will go very high. So, and this is that point is your fault point, which is that T1. So again, initially assume that it was 1.0 per unit value. Everybody, can you follow me?
I have a question, please.
Oh yes, Othman.
So you said we don't have a governor and IVR. Is that like an assumption, or it's not shown in the schematic? That's
No, because this is the squirrel cage induction machine. So the problem was not about synchronous machine. So let me take you that picture. You see, this is the IG, induction generator. So we are discussing number 2. We are not in the figure 1, we are discussing figure 2. So it looked like the same, but the figure 1 has SG, synchronous generator. Synchronous generator will have AVR governor. But because this is induction generator, it has only the terminal capacitor. But it does not have AVR and governor.
So, oh, my bad. Because I saw it as a synchronous generator when I read the problem. I didn't notice it's induction.
Oh, no, the first one was the synchronous generator. Yeah, you see?
Yes.
Yeah,
That's
yeah,
why,
yeah.
yes.
Yeah,
Thank
okay.
you.
And then now we are, I mean, both figure look like very same, but the difference is this is SG and this is IG. Yeah, that's the difference. Okay, so now, and then I think I am taking you to the board. For everybody, see, if the input torque of the generator varies randomly, then now would the voltage and frequency of the generator be affected? So now, I mean, and we are assuming that for that second part of the question, there is no fault involved. Just the input torque is varying. So I'm taking you to the board once again. You see, we are discussing this thing. Now, if there is no fault involved, but the input torque is varying, so for example, this is your T and this is your V, and then normal condition, the voltage is going in that way. But if the input torque varies randomly, then there will be some sort of fluctuation. There will be continuous fluctuation in the voltage profile. The same thing. I mean, it is just the input variation. It is not the fault. That's why it will not go downward. It will just oscillate. Now it depends on the input torque variation. If you see, for example, little torque variation and then again here is big variation, then accordingly there will be fluctuation, because voltage will follow the input torque pattern. Accordingly it will vary. The same thing will happen for the power curve. We are assuming that initially it was fine, but then like it is oscillating. Whatever, assuming that this is the pattern of the torque, it will follow the pattern of the torque. The same thing it will happen your speed, because that torque is imposed on that speed mainly. So initially it was fine, but then it will also oscillate. This means that all three parameters will oscillate. So therefore, see the difference. Left side, we assume that there is fault. So let me write down fault, but no input variation. In this case, no input variation. But in this case, for the second case, no fault, but input varies. Yes, that is the two condition. So everybody, could you follow me?
Yes, Dr. Ali.
Yes,
Yes.
Dr. Ali.
Okay, thank you. So now I already saved. So again, you can see in the video later. So I am stop sharing, and then I am taking you to that question. Now we are done with the second part. For the third part, how can you ensure the constant voltage and power at the consumer's end? We're assuming that, okay, something happening, input torque is varying, whatever the input source is, it is varying. Consequently, you notice that there will be fluctuation in frequency, voltage, speed, power everywhere. So how will you get the constant? So what you need? You need to use the energy storage device. You need some compensator. At the grid point, you need to connect the energy storage that will compensate those fluctuations, because energy storage can work both in charge mode, discharge mode. So by consuming power, by sending power, it will minimize and it will provide your required power. So therefore consumers will not be affected. You see, the consumer's goal is to get always constant voltage and power. So this is the common nature. So therefore, as a customer, we don't want to know what is happening this side. My goal is to get constant voltage and power. So therefore, it is the duty of the distributor or utility company to put energy storage device so that the customers are not affected. Customers get. So therefore, answer would be, I can ensure the constant voltage power at the consumer's end by connecting energy storage device. So everybody, could you follow me?
Yes, Dr. Ali. I have a question.
Okay.
So I'm a little bit confused. I mean, when we vary the input torque,
Okay.
then does it also change the voltage?
Yeah, but there will be some fluctuation in voltage as well. You see, in one class I was showing you that voltage is proportional to torque squared.
Oh, yes. Yeah.
Yeah. So the voltage will also be affected.
Okay. Thank you, doctor.
Oh, no, of course. Now, there is one capacitor, you see, connected. That is 24 hours working. That is 24 hours working. But this is for the normal situation. Normal situation means its function, because for its operation, induction generator needs the power, reactive power from the system. So that is compensating this capacitor. It cannot do beyond that. This means some additional fluctuation is coming, which is from the input or the fault happened. So this capacitor cannot do, because you see this is fixed. It does not have any controller involved. For example, braking resistor have thyristor based control. It is fixed. So when this system is installed, this generator, that I'm talking about real practice. At that time, it is calculate what should be the capacity, how it will fully compensate, so that there will not be any voltage drop during steady state condition. So it is that function that it will try to hold the constant voltage during steady state condition. But these are the some transient situation. Fault is definitely transient, and input torque is varying. So it cannot do anything. It will only compensate the always it is injecting the reactive power. It is always taking the reactive power from the system. That is its function. It does not have controllability beyond that point. So is this fine?
Dr. Ali,
Yes.
how can we control the varying torque for the generator?
Oh, so there can be some mechanical arrangement with the help of some mechanical controller. There is torque speed converter, torque speed controller. You can do that, but in most cases it is controlled from the electrical side. So that's why in this case it is the energy storage. Your input torque, because input torque is coming from your source, from your fuel source. For example, think about that. It's a wind generator, and that wind, because wind speed is varying, you have no control. Now on the mechanical side, once it come on the shaft, the variation, then in case of wind generator, there is pitch control system. You can control that. Or if you assume that this is not the wind generator, that input variation is coming from other sources, then either you can control mechanically with the torque speed converter, or you can look only the electrical side. So it does not matter what is happening on the mechanical side. Let the input torque applies and get the output affected. Then I will fix my problem. So in that case, energy storage is the device.
Okay, thank you.
Okay. So you assume that input torque is coming due to the source, fuel input. So there you have no control. As I said, if it is wind speed, then you cannot control the nature. But you can do something in mechanically and then electrically. Yeah. Okay, so moving forward, you see the question number 3. Everybody see. Consider a 3-line to ground fault occurs at point F1. This is the point F1 in the following power network shown in figure 3. You see, in this case now I am combining. So, so I said hybrid power generation system. So far I showed you, okay, there is synchronous generator only, and then there is induction, but I have coupled it. I made it hybrid. There is both SG and there is IG together with the capacitor. This is the arrangement. And they are powering the same infinite bus. Customers are connected here. Now, what is the question? Question is, how will the voltages at the terminals of both generators, SG and IG, be affected? To improve the overall voltage stability, which of the following devices would you choose to install at the secondary side of each transformer? Explain your answer. So the meaning of the question is that because there are two generators, definitely if you just put only one thing here, it cannot solve the problem here. Or if you just put one solution, induction generator, you did not look SG, that will also not help. I mean, it will help somewhat, or it can provide the local stability, but it cannot maintain the overall voltage stability. So which of the following devices would you choose?
I think switch capacitor and
Yeah,
STATCOM,
switching capacitor.
and STATCOM as well.
Yeah, so right. So
Yeah,
therefore,
STATCOM.
yeah, so the thing is that what would you like to put at the secondary side of the SG? There are two transformers. One is the upper side. So that is the question to install at the of each transformer. So what would you put? Which one you would put at the terminal of SG and which one would you put at the terminal of IG? I mean, you can pick up multiple devices, no problem. Like as you said, switch capacitor and STATCOM. So Manoj, what did you say? Where you will put switch capacitor STATCOM?
I put in the secondary side of the induction generator,
Okay, so
switch capacitor and STATCOM, and I will put a switch resistor on the secondary side of the synchronous machine.
yes,
I mean that.
exactly. That's the appropriate answer. So now, like for IG, definitely we will not put two devices together. No, we will not put switched capacitor plus STATCOM because it will be too costly. So you can say that, okay, we can put either of the device, switch capacitor STATCOM, but the STATCOM performance will be the best because STATCOM has the robust control strategy inside it. Switch capacitor is just normal switching. So definitely it will help improve, but STATCOM will be more robust. So you could say that at the terminal of IG, I will put either switch capacitor STATCOM. However, the STATCOM performance will be better than the switch capacitor. And then, like as Manoj said, at the terminal of SG, I will put switched capacitor because that is the SG. Main thing is to control the active power. So I will put a switched resistor. I will not pick up switched inductor neither at the terminal of SG nor at the terminal of IG. Everybody, could you follow me?
Yes,
Yes, Dr.
Okay. Oh, and then
Really?
there is the first part of the question. How will the voltages at the terminals of both generators be affected? Now, the fault is the same, fault point is the same, and it is the integrated network, a hybrid network. So definitely both generators will be affected. So when I'm asking that, how will the voltage of both generators look like? So you can say, because synchronous generator will have AVR and governor, so therefore its voltage, definitely voltage will go down for SG also, but it will come back after some oscillation. It will come back to the original stable condition. In case of IG, because it does not have inherent like control system like AVR or governor, in this case, it will go down, and depending on the type of the network and then the fault situation, it might or might not come back. In most cases, it does not come back. Like always, voltage collapse happen in case of the induction generator. So therefore, that will be the difference for the voltage profile. You will say that in both cases, voltage will go down, but synchronous generator, it will come back to the original position because it has AVR governor. In case of IG, it may not come back. It might be fully collapsed. That is the difference, and that is the answer to the first part of the question. Okay, and now another question. To augment the power system stability, sometimes series connected means and sometimes parallel connected means are used. Is there any major objective behind their usage? Explain your answer. Okay, so meaning of this question is that you remember, for example, in on previous question, I was asking this one, series register. This means there are example in real practice also that series register can be connected. Also, I mean, few classes later, we will be noticing fault current limiter. Fault current limiter basically a series reactor that is connected in series. There is thyristor controlled switching capacitor. There are static synchronous capacitor. Typically, those are connected in series. And there are parallel connected device. For example, that thyristor based braking resistor, it is connected in parallel. Sorry, the energy storage device that is connected in parallel. I mentioned that STATCOM that is connected in parallel. This switch capacitor that is in parallel. SVC is in parallel. So this means the meaning of the question that to augment the power system stability, sometimes series connected means, and sometimes parallel connected devices are used. So what is the philosophy behind that? Is there any major objective? That is the question. So could you guess that what could be the, what is the difference between series connected device, parallel connected device? I mean, both will improve the stability. The goal of the both, objective of both is to improve stability. But what is the driving force behind the choice of this one versus this one? So what it will control and what it will control?
May I try, please?
Yes.
I think maybe in the series connection, we will get the same current. So if we need to get the same amount of current, we can do the series connection. But for the parallel connection, we will get the same voltage for each branch. So
Okay.
I think maybe that's why.
Yeah, I mean, you are there. So the thing is that series connected device will control the current, right? So series connected device will reduce the magnitude of current, fault current. And in that way, they ensure the stability. So then you are right, parallel connected device, because parallel thing, so voltage is the dominating. So that's why it will control the voltage and the, as well as the active power. So that is the motivation. So sometimes in some cases, series connected device work better. It depends on the network topology, a specific location. That's why in some power grid, or I mean all over the world, as a protection means, you will be noticing there are series connected device. Like there is fault current limiter. Its name is fault current limiter. Therefore, clearly that is reducing the fault current magnitude, and then the voltage, active power, everything is coming back to the original position. According to this concept, for parallel connected devices, because like as Amani mentioned, okay, it will control the voltage first, and then active power, and the system stability will come back. So that is the objective. So you will simply say that series connected means will control the current flow, and it will reduce the high magnitude of current during fault, and parallel connected device will control the voltage and hence the active power. That is the answer. Everybody, do you understand?
Yes, sir.
Okay. Now the next slide. Here I think there is one numerical problem, and after that I think there are another 3-4 numerical problem. Okay, now let's see the question number 5. You see like all like stability and stability question, lots of things. While the voltage stability and transient stability of a power network are treated differently, and different control means can be used to maintain their respective stability, is there any unique control means to maintain both types of stability simultaneously? So you know the from the definition that we looked in the early of the semester, voltage stability refers to the voltage situation. So this means that according to the voltage stability concept, you have to maintain the voltage at each and every buses of the network. So for example, your speed might come back, frequency might come back, but due to some reason, voltage might not come back. But you have to maintain the voltage. That is the voltage stability, maintaining the voltage. And then transient stability, basically this refers to the rotor angle, the delta angle, or the speed deviation change. That is the actual definition of transient stability. I mean, both are interrelated, but still in the literature, both are treated differently. And accordingly, different control means are used. Therefore, for example, to maintain the voltage stability, you might choose the capacitor, or you need to choose the SVC or STATCOM. On the other hand, transient stability means you can choose braking resistor, energy storage device, that fault current limiter. So it depends on the system and the nature. Before installing the real world system, it is the huge analysis was made. Huge analysis was done. Huge study was made whether to put the STATCOM or SVC or braking resistor or fault current limiter or energy storage. So by looking the natural profile, sometimes voltage stability protection means only put. Sometimes only transient stability cost compensations are put. But the question is there any unique control means that will maintain both type of stability simultaneously? Is there any unique device? That is the meaning. Like for example, you can say I will be putting both capacitor as well as the braking resistor, or I will be putting both fault current limiter and STATCOM. Definitely that will work. But that is not the question. Question is there any unique control means that can maintain both types of stability simultaneously? What is the device that can ensure both stability, that both voltage and then the speed, frequency, everything will come back. So therefore, can anybody guess what could be the device?
Dr. Ali,
Resistors.
Guess. Yeah.
can we think about SCADA since it's the brain of the entire system that will control everything?
Yeah. Everything. So what you are actually asking?
No, I'm saying like, since SCADA is the brain of the system, can we think about it as a device that can control both voltage and stability and transient stability?
So you are talking about the SCADA, right?
Yes. Since like the main computer.
Definitely SCADA is the master controller, and that is monitoring the overall situation. Definitely SCADA is working behind that, but the thing that SCADA is the master controller. So SCADA will monitor the situation. For example, for this, I mean, you are partially right. In real practice, this control will be performed through the SCADA. But the question was not it is the SCADA, because SCADA will monitor the situation. SCADA will make a decision and send the decision to the control means. What is that control means? That is the question. So therefore, you are 50%. You are 50% right that SCADA will control. SCADA will control what? What things will be controlled by SCADA? Because SCADA is the decision maker. Yeah. It is 24 hours maintaining the overall situation. So therefore, you are 50% right. Then what can be the device? Therefore, I think someone told the energy storage, right?
Yes, Dr. Ali.
Yes. So therefore, like Othman, now the SCADA will send the message to the energy storage device. Okay, then let it work in this situation, because energy storage has the capability to control both active power and reactive power. So the voltage stability mainly refers to reactive power control. Transient stability mainly refers to active power control. So therefore, that can ensure both stability. So that is that unique control device, that you don't need two different devices. You don't need the combination of resistance and capacitance. Not a separate device. It is together, which is the any energy storage device. I mean, these days, battery energy storage, supercapacitor energy storage, magnetic energy storage, pumped hydro energy storage, thermal energy storage, compressed air energy storage, all have the unique capability. And also there is another device, FACTS device. It is called flexible AC transmission, UPFC, Unified Power Flow Controller. You can write down UPFC, Unified Power Flow Controller. Let me write down that keyword. So everybody please write down this keyword. UPFC. It is called UPFC. That stands for Unified Power Flow Controller, UPFC. It's a FACS device, flexible AC transmission system device. It has the capability to control both. It is similar to that energy storage. I mean, it is not actually the energy storage, but it is similar to energy storage. It is called Unified Power Flow Controller. If you just Google this on UPFC, you will get hundreds and hundreds articles. It is very well known and well matured technology, UPFC. It's a kind of the FACS device. It is called FACS. Sorry. FACS, flexible AC transmission system device. Let me write down this. Flexible AC transmission systems. It is called the FACS. This one, flexible AC transmission system. Briefly, it is called that FACS. So this is that category. I mean, there are lots of FACS device. So UPFC is one of that. But among the FACS device, this UPFC has that capability to control both active and reactive power. That's why you might choose this unique device to maintain that global stability, simultaneously the voltage stability and the transient stability. That is the meaning of that question. So let me take you there. Venkat, in your system, I think you have used the FACS devices, right, in India? Venkat?
Yeah, yes, sir.
Yes, because you
The
work
substation.
yeah, substation, because you work in power company. That's why I'm drawing your attention.
Yeah.
Okay.
Yes.
Okay, let first cover the question number 7. Then there is no conceptual question today. There are several numerical problems, 6, and then I think another 4 problems in the next slide. Everybody read question number 7 first. A 3-phase to ground fault occurs at point J. Again, the same system. This is IG in the following induction generator system. Then how can a static synchronous compensator help maintain stability of induction generator? Also, what is the difference between the STATCOM and then capacitor C used at the terminal of the induction generator? Now, meaning of the question is that because this is induction generator and fault happened and voltage will collapse down, so definitely we have to compensate that reactive power. So you need reactive compensator. So that's why it is asking about STATCOM. So for the first part, how can a STATCOM can help maintain stability? So you will be saying that STATCOM will be connected at the grid point, at this point, at the grid connection point, and that will control the reactive power. And in that way, it can help maintain the stability of the generator. So therefore, the answer is STATCOM will be connected at the grid point and it will provide the reactive power support that will compensate the inductive effect in the network and it will help maintain the stability. Now, this means that STATCOM is a reactive power compensator. Now that's why next question I am asking, then what is the difference between the STATCOM and the capacitor C used at the terminal? So if the STATCOM can control the capacitor, sorry, the reactive power, then why not capacitor not helping to maintain the stability? So how would you answer that? So STATCOM, you see STATCOM you are connecting at the grid point and that is helping improve power factor because it is providing the reactive power support. Very similar function to a normal capacitor. That's why I am asking then what is the difference between that STATCOM that will be connecting here versus this capacitor? So how would you like to answer? So Lakshmi,
Dr. Ali.
yes, so what could be the possible answer? So the why I'm asking, because like this capacitor can also provide the reactive power. STATCOM also provide reactive power. Of course, you know that STATCOM is the improved control version. It has a robust control system.
System, yeah.
Sorry?
You said that STATCOM is the robust controller compared to capacitor.
Yes. That is, of course, that is answer. 50% you are there. So everybody see the difference is that this is only for the steady state condition. I mean, it is working 24 hours. During fault condition, it is working. But you see, it does not have any control capability. It is fixed capacitor. So therefore, your answer would be that although STATCOM and capacitor can both control reactive power, but this capacitor C here, it is designed to handle the steady state situation only. It does not have the capability to handle the fault situation, because during fault, it cannot change its value. It is fixed. There is no controller. Like for example, if it is 100 microfarad, normal condition, it cannot be 2 farad. You cannot change it. If you could change it during fault condition, then this would be enough. But it is fixed. So that's why it is providing reactive power to compensate the steady state condition. Its function is to provide the rated power, rated voltage during normal condition only. Its function is just to compensate the reactive power that is needed for the system. That's why you are connecting additional means, which is the STATCOM here. Because during fault for the induction generator, there is huge voltage drop and it starts drawing huge reactive power. That's why this capacitor is not enough, because you see it is uncontrolled. It is designed only for the steady state situation. I mean, it is working. I mean, of course, it is working. It has the role during fault condition, but it is not enough because it is fixed in design and it does not have any controller. So it is not adaptive. It is not adaptable to the changing situation of the network. That's why you are putting STATCOM. So therefore, your answer will be that capacitor C is mainly for the steady state situation, and the STATCOM is only for the transient situation. The thing is that, and also you will be telling that once the system stability will be maintained, STATCOM will be switched out. STATCOM will not be in the circuit. It will be switched out, but this capacitor will be in the circuit always. So therefore, in summary, STATCOM is for transient situation and capacitor is for steady state and always. So everybody, could you follow me?
Yes, sir.
Yes, that is the thing. Lakshmi, is this fine? Okay. Sindhuja, are you noting down everything?
Yes, Dr. Ali.
Okay. Okay, now please everybody, you solve number 6. Everybody please take your pen and paper and solve question number 6. This is numerical problem. Before we discussed a lot about those things at the beginning of the semester, synchronous generator, induction generator, and then the slip. So read the question. A single phase 2-pole squirrel cage induction generator is providing power to a 2 kV 2 Hertz inductive load and is driven by a 3 horsepower DC motor that develops a torque of 7 Newton meter. If the slip of the generator is minus 0.0, then calculate the system frequency. System frequency is not given, that you have to find out. Also, how much reactive power will be drawn by the inductive load. So first, can you draw a schematic, and then that will help you to get the answer. So see, you have an induction generator and you have a DC motor. So DC motor is the prime mover for the induction generator. And also there is an inductive load. Okay, so So the picture will look like this. Let me draw the brief schematic and then I think you will be able to solve. Let me erase all of these things. Okay, so everybody see, this is the induction generator, labeled by Ig. Okay, and this Ig it is connected to the grid, but here there is an inductor at the terminal. This is that inductor. I think it has 2 Henry value that we noticed. Okay, and how much voltage we noticed? I think 11 kV. We are going to the problem. Okay, so this point, this is the grid point. Then it is connected to the rest of the system. This side is the grid. Now, this induction generator, of course, it has the shaft. That shaft is moving, but that shaft, it has a what it says, it has a DC motor. Yes, so meaning that DC motor is working as the prime mover for this induction generator. They are sharing the same shaft. So this is the omega shaft speed, which is the common to both DC motor and the induction generator. So under that condition, I think, and then the slip value for this one is given. I think slip value minus 0.01, that is given. So everybody, please you draw this basic schematic in your paper. First you draw this thing. So once you are done, then let me know. Then I will go back to that problem statement. So you see that this is working as the prime mover. This motor, and its shaft is coupled to the induction generator. It has a slip. It has a terminal voltage, and a load, inductive load is connected, which is 2 Henry. I think we are going to the problem, and slip value is given. So the question is, I think the question is, what's the frequency? What's the frequency? Frequency is not given. That is one question. And second question, what will be the reactive power here? How much reactive power will be drawn by this inductive load? Yes, that's the two questions. This means here you have to find out QL. What is the reactive power? Is everybody fine? Can I go back to that problem, or still you are drawing?
Yes, sir, it's done.
Oh, you are done?
Yeah.
Okay. Manoj, come on, everybody done?
Yes, sir. Probably.
Yes, sir.
Okay. And then again, you can see in the video. So this is, I already saved. Okay. Now, okay, now please read and then solve. So therefore, induction generator has 2 poles and 2 kV. Oh, sorry, I wrote the wrong number for the voltage. It says 2 kV. Please change the voltage of the induction generator. Terminal voltage is not 11 kV. Please change that number. Please use 2 kV. 2 Henry inductive load. So put the inductor value 2 Henry. And for the DC motor, left side component, put the 3 horsepower there. I did not put anything. That is the shaft output power, and that develops torque of 7 Newton meter. Now slip of the generator, definitely this is for induction generator that I wrote. Then calculate the system frequency. System frequency is missing from here. So how to calculate system frequency? And how much reactive power will be drawn by the inductive load. So can you guess what to do?
So I think we have to find the NS first, synchronous speed, by using the slip formula, because we can find the rotary speed by using torque power equals to torque multiplied by omega.
Exactly, yes.
And then from that we can find the NS, and from that we can find the frequency 120 F by P.
Right. So everybody see the slip is given. So can you remember the slip equation? Slip is synchronous speed minus rotary speed over synchronous speed. So this means that in the slip equation, I mean, let me give you the hint. Hold on a moment. You see, what is the slip equation? So slip is, everybody see, then I think you will get it. This is synchronous speed minus NR, rotary speed, and then synchronous speed here. So this means this is that slip value minus, this will go there. Now, you don't know NS, because NS is, sorry, let me change this number. This is 2 kV. This is 2 kV. And this is 200. Let me put all the things. 200. Okay. So therefore, but you know that NS is, what is NS? NS is 120 F over P, right? That is the synchronous speed. So, and then this is not for this one, this is for the induction generator, this equation. So therefore, everybody say, look the slip equation, your slip value is given, and you are not able to get the NS, you are not able to plug in here because you don't know the frequency. That's the question. But its pole number is given for the induction generator. So, but if you know the NR value, what is the NR? NR is the speed of this shaft. This is the shaft speed, NR. So therefore, for the motor, the information is given. You see, its power value is given, its torque value is given for the motor. So therefore, with the help of the motor power and torque equation, you can find omega. And that omega is in radian per second. Then next time to use in this equation, and that is actually your NR. The speed on this shaft, that is the NR in this equation. So therefore, from the motor power and torque information, this thing will come. And then once you get the NS from here, then you will get the frequency. And once you get the frequency, then what will be your reactive power? What is your QL equation? So
E squared by
yes, so it is
XL.
right. Sorry. Oh, let me just a moment. That is V square over XL. Everybody see? That is the reactive power equation for this one, for inductor. XL. And what is XL? XL equal to omega L. XL equal to 2 pi FL. You see, therefore, to solve this part, definitely you need the help of frequency. Therefore, unless you can find out this frequency, you cannot find out this QL. So therefore, everybody note down this QL is V square over XL, and XL is 2 pi FL. And you write down all the equation I explained, and then now you go back to that problem. Everybody, do you understand and did you note down all the equations?
Yes, sir.
Sindhuja, Lakshmi, are you fine?
Yes, Dr. Ali.
Okay. So you note down. Then now I am going back to that problem.
So it's 50.38 frequency,
That is the frequency. That's right. Yes.
and QL is 6.318 kilobar.
Yes, that's right. Both are right. Yes. So absolutely right. So therefore, everybody try. Your frequency should be 50.38 hertz, and reactive part should be 6.32 about kilohertz.
Hello, Dr. Ali.
Yes.
Yeah, I got the same result.
Frequency 50.38
38 and Q value
6.32.
6.32 kilobar.
Okay. Very good. Amani,
Yes, Dr. Ali.
did
I'm
you?
still working.
Oh, okay, okay. But you understood the procedure, right? Yeah.
Yes, yes,
Okay.
I got the process.
Okay, okay. So everybody, it's just the matter of calculation. Make sure that you are getting those values. Lakshmi, did you get frequency?
Yes, Dr. Ali, I got the values the same.
Oh, the 50.38. Okay.
50.39 and XL and Q I got the values.
Okay, and then how much is the QL reactive power?
6318.
Oh, 6.18.
Yeah.
6.18 kilobar.
631. Yeah.
6.18 kilobar because it is Q, so unit should be
Yeah.
kilobar.
Yeah, kilowatt. Yeah.
Oh, okay. The Sindhuja, where are you? Venkat?
Yes, Dr. Ali.
Okay.
I'm working on it.
Ah, okay. Do you need to see that whiteboard once again, or you are fine?
I'm fine, Dr. Ali.
Okay, okay. Venkat? Has Venkat left? He is not responding. So Amani, are you done or still calculating?
I got the frequency 33.6. Because of that, I'm sharing my results for the speed on the chat. Can you please take a look on them, please?
Just a moment. I stopped sharing. Let me allow you. Okay, you can share your screen.
I'm putting in the chat. I'm using the chat.
Okay. Just a moment. Oh, inner value 2036 RPM. No, that is RPM, right?
Yes.
But that is wrong. That is not the right.
I use the power, the horsepower, and the torque to find the speed.
Yeah.
For that,
yeah.
go ahead,
So,
sir.
what was in radian per second that you got?
I got 319.71.
That is right. After that, you convert into RPM. That is
Yeah.
not right. That is not right.
Okay, maybe that's my mistake.
Yeah. Please check that one.
Yes, I got something different, completely different.
Yeah. Can you tell me what number you got?
Yes, sure. I got 3054.55.
Yeah. Now you are there. Yeah, like kind
Okay.
of 3053, and now you are fine. So now you go ahead.
Okay, thank you.
Okay. Actually, I think. Okay, so here you see like my calculation. I did it. Amani, yeah, location.
Yes, Dr. Ali.
Yeah.
Mhm.
Sindhuja,
Yes, Dr. Ali.
Yes, so here you see, I have calculated this one. That is that schematic I was showing. And I'm first calculating the omega, the 3 horsepower for motor, and then torque, power over torque. So I got this 319.7 on radian per second. I converted into RPM, and that is my NR in the slip equation. So let's see my calculation. I put this number for NR, slip value is given. So after calculation, finally I got frequency 50.38 hertz. Therefore, in case you have any mistakes or anything missing, so you look this one. And then once you got that frequency, there, as I said, QL is V square over XL. That V value is 2 kV, which is given. So 2 kV square over 2 pi FL. So to FL value is 2, and F value is this one, 50.38. So I got 6.32 kilowatt. So Amani, did you finally get the frequency this one, or is still calculating?
Yes, Dr. Ali, that was my own mistake, the NR value.
Okay, now you got the right value.
Yes.
Okay, and then how about Q?
I'm still working on the Q.
Okay,
Just 1 second.
okay. So Sindhuja, did you get this number? Just look the calculation and then use your pen, paper, and calculator. So are you getting the same number?
Yes, Dr. Ali.
Okay, and then how about Q? This one, second part.
Yeah, yeah.
You
Yes, I
got the
got it.
same number? Okay,
Yes.
fine. So Amani, is it matching with this one?
Almost there. I'm sorry. I'm very slow. But
Okay.
I got the idea. If you would like to move to the next question,
Oh,
so I'm
okay.
good.
Okay, so you wrote down the equation, right? Yeah, so you can do, yeah.
Yeah, I got everything.
Yeah. So, and then this will be available on eCoursera, so you can see later calculation. Now there are, 3 more problem, but I think we'll get time to do the first one. Look, everybody, the first one, number 8. A 3-phase 4.17 kV 60 hertz Y-connected cylindrical rotor synchronous generator has a synchronous reactance of 2.2 ohm per phase and a winding resistance of 0.15 ohm per phase. If the load connected to the generator is 950 kVA at 0.85 lagging power factor, then determine the per phase induced voltage. So this is with regard to that synchronous generator. So synchronous generator has the armature coil or stator coil that has reactance of 2.2 per phase. And the winding resistance means the resistance value in the coil is 0.15. And again, it is per phase. That's why I'm asking answer in per phase. If the load connected to the generator 950 kVA at 0.85 lagging power factor. So that generator is providing a load. That load has 950 kVA. It's apparent power, and this is the power factor. And 4.17 kV is the line-to-line RMS voltage available at the terminal of the generator. Based on that, what is the per phase induced voltage? What was the voltage generated inside the coil? That is the induced voltage. Keep in mind that 4.17 kV that is available at the terminal of the generator. That is not the produced voltage or induced voltage. That is the question. So let me draw a schematic, and then I think it will be clear to you, and then you do. Let me draw a schematic. Okay, let me turn off this thing. Okay, what actually it is asking, you can draw with me. This is that generator, because it says per phase for one phase, and then it has that synchronous reactance, and then winding resistance. This is the terminal voltage of the generator, and then because it has the load, so this is that load current, which is the this side, it is the load. Load is connected. Okay, and then this is that induced voltage. Okay, and then this is the labeled synchronous reactance, and this is the winding resistance RA. So therefore here, if I write down the expression, your EA will be, you just write down the equation and then you will be able to do that. So terminal voltage, you see. So this is the voltage, and there is some drop through this component and this component. Only then I am getting the terminal voltage VT. So therefore VT plus, you see, IA, and then RA plus JXS, synchronous reactance. Yes. So everybody write down this schematic and then this induced voltage equation. This is called that induced voltage. Induced voltage. And your VT is actually, you see, the VT is, it is called the terminal voltage. Yes, this one. So that is the VT. So VT is the terminal voltage, and EA is the induced voltage. And XS is the synchronous reactance, and RA is the resistance, and I is the load current. So you see, this current is going through the load. So you have to, from the information, you have to find out the IA, how much current is going to the load. I think load kVA is mentioned, probably it was mentioned 950 MVA. MVA or kVA, we are going to the problem. So everybody, have you note down this equation and this diagram?
Yes, doctor.
Okay. Amani?
Yes, already I wrote it down.
Okay. I think 950 was the kVA probably. So load kVA was 950 kVA, and I think power factor was 0.85. 0.85 lagging. Yes. .85 lagging. Okay, so then at least you write down this equation, then you'll be getting it like VT plus IA, RA plus JXS. So you have to find out EA. So therefore now I am taking you to that problem. Now you read this one. So 3-phase 4.16 kV 60 Hertz Y connected. This pin, you see, this is the terminal voltage VT. But keep in mind, this is line to line voltage. This is not the phase voltage, but the equation that I showed you, that is per phase. That is per phase system. So you have to convert this voltage into per phase. And then the other information is given. Synchronous reactance, XS value in that equation. and RA value is given. Now IA value is not given, which you have to find out from this expression. Load connected to the generator is 950 kVA, 0.8 lagging power factor. So power factor is given and its kVA is given. And of course, that is the terminal voltage that appears across the load. So based on that and using that equation, can you calculate the per phase induced voltage? So keep trying. So everybody see, you have to find out the IA value from this information, 950 kVA, and the voltage information. Using these two information, you have to find out the current value. And keep in mind, this is the three-phase system, but you are finding the per phase induced voltage.
Dr. Ali, I got EA value 3.34 kilovolt.
3.34. It looks like some different number. In your result, do you have the angle, phase angle?
No, I didn't use that.
This means I think that is the problem probably. I mean, in answer, you can tell the only magnitude, but when you will be calculating, definitely there should be angle.
Yeah, it's a three-phase.
Yeah, there should be the phase angle. After calculating the current IA, you have to, everybody listen. Once you will be finding the current IA, then immediately you have to put the angle together with the magnitude of the current. And that current, that angle will come from the power factor, you see, 0.85 lagging power factor. So find out what is the angle for that. And then because it is lagging, so angle will be minus. So this means that first you have to find out the current. And once you get the magnitude of current, then you have to put the angle with it. And that angle will be minus because it is lagging. So from this information, you will be able to get the current value, sorry, the angle value. And then in your rest of the calculation, always you have to keep the angle. Because you see the synchronous reactance, if you see the equation that I have written, there is J. So, and then winding resistance, it is just R, but this is JXS 2.0. So that's why ultimately you will have a magnitude and together with the angle. In that way, you have to express the voltage. Then you will not be missing. So is anybody getting or? So once again, you have to consider the angle with the current. And that angle is this angle corresponding to this 0.85 lagging power factor. And in the calculation, you must take into account that angle. Otherwise, you will be deviated much from the answer. Kamana, did you put the angle next time?
I'm working on this, Dr. Ali.
Oh, okay, okay.
So what is the current, Dr. Ali?
Current, how much you got current value?
I got 131.53.
That is right. That number is right. But then what I am saying, that is your current, but with that current, you have to consider the angle.
So the angle is,
And
okay.
with that angle, you have to put in that equation, EA equation, including the angle. And that angle will be minus because lagging power factor.
True.
With
So
that,
it's,
then you have to go ahead and then you have to complete the calculation, and you should be getting a magnitude together with the angle, the induced voltage. But to get the correct magnitude from the beginning, you have to properly consider that angle. Otherwise, you will be deviated much.
yes, yes.
Okay, so what you can do, everybody, please keep trying. Okay, yeah. You keep trying, and in next class you let me know. And also then do problem number 9. Everybody see problem in problem number 8. If the power factor would be 0.85 leading as well as unity, how would the value of induced voltage change? The same problem, but you consider 0.85 leading instead of the lagging power factor, as well as power factor is 1. So in all three cases, what is the induced phase voltage you are getting? So therefore in the next class, you let me know. Okay, at least everybody tried now 8 and 9, and the next class you let me know. And if possible, you can solve number 10 at home, and then you let me know.
Yeah, sure, Dr. Ali.
Yes. Okay, everybody. So please, you keep trying. You keep going. I gave the hints, and then once you are done number 8, do number 9. Where the power factor is leading, and power factor is, so there will be 2 more results. So how the value will be changed, then you can see. And if possible, try number 10. Okay, so with that, I am everybody. I am stop sharing. I think it has been about 7 already. We're done. You please keep trying.